thank you very much, and thank you, Alex and ACES, for inviting me over here to do this, which is great. We love evangelizing our product. So let's dive into some of the practical things, and then we'll dive into content afterwards. So for the edification of anyone who hasn't been on a software carpentry or anything like that, I'm about to pass out some high-tech aids to this afternoon's proceedings. So what I'd like everyone to do is take one green and one, well, pink, red label. And the reason why you need a green and a red label is because we're going to do this tutorial hands-on with people actually doing stuff in Firedrake. And this is how we're going to communicate as a room about where we're up to. So the general rule is if you are like happily working away or happily listening to what I'm saying, then you just don't have anything up. You have these two stickers sitting on the desk in front of you. If we're trying to do something and you're in trouble and you need help, what you should do is you should stick the red sticker onto the top of your laptop screen so that you don't have to sit there like an idiot with your hand up. And I will come running around, and Alex has offered to help a bit as well, and maybe there are some other people in the room who've done a bit of Firedrake or Phoenix who can help you out with that. Similarly, when we're doing these exercises and you are doing the exercise and you're done, you're bored, you're waiting for me to go on, well, you should just put the green one up. So when you're done with the current exercise, you put the green one up, and then I can see how the pace of the room is going and at what point we should move on to the next thing. And it won't always be waiting for the last person. We'll sort of go at the pace that the room as a whole can averagely take. So that's admin issue number one. So admin issue number two. So the way we're going to do the tutorial is we have Firedrake set up running on a Jupyter Hub instance on Azure, which is Microsoft's cloud service. And so in principle, what happens if things are going well is if you point your web browser at firedrakeproject.org/Aachen, just for this afternoon, that will redirect to the server, and that will hopefully cause something that looks a lot like this to spring up on your screen. Now, in order for that to work, Amazon Web Services, which is somewhere around here, the West European dot is really quite close to Aachen. Sorry, not Amazon, this is the other one. Microsoft are going to pull a container containing a complete Firedrake instance from Docker Hub, and that can take a few minutes. So I want everyone who's got a laptop that they brought along who wants to play along to put that URL in now, because what's quite likely to happen is you'll get this blue bar that will stop for several minutes until it gets there. And also then, if you are currently looking at a blue bar, waiting for that to come up, I'd like you to stick up your red tag so that I can see who we're still waiting for who's not got one loaded. So once the thing has pulled, that's true. But while you may well have to wait several minutes to pull. So if you're looking at a bar at the moment waiting, put up your red one. If you are already seeing this, please put up your green tag so I can see how far along we are. Wait, this is working way better than it did at CSE. That's totally awesome. Okay, I'm just going to wait while this filters around there, but it looks like we are actually up and running as a room, which is so good. It took us 15 minutes in Seattle to get this far. Where were we? Spokane. So what are we going to be doing here? So Firedrake is a piece of finite element software, and the world is full of finite element software. Why on earth do we need people working on finite element software? Why do we need new finite element software? Well, the guts of the matter here is that what you do when you make a simulation based on a PDE is you compose together a really quite deep stack of mathematical operations. So somewhere out here you have an actual physical system, and someone who's probably an expert in that area of physics or engineering or chemistry has thought of a PDE. And now someone who knows some numerical analysis has worked out a discretization, and in the finite element land, that basically means they've worked out which discretized function spaces would produce a stable and accurate stupid version of this, and they've worked out all the correct boundary conditions, which are miserable. And then what you have to do is turn that into a series of loops over cells, and in each cell we have to loop over the test functions and the trial functions if we're assembling a matrix, and do an integral using quadrature, and then the result of that has to be splatted out into a global sparse matrix or a global vector, and the result of that needs to be fed into a linear solver. And that was just for a linear problem. Right? So each one of those steps is something that you can quite happily do your PhD in. And the expertise required to do them well is really quite advanced. And it keeps changing as well, because people keep mucking the hardware on us. So now if we're going to go fast, that innermost loop has to be vectorized. And that's really pervasive, because that means that every single operator that results from every single term in every single PDE needs to be vectorized right down in the middle. So the conventional way of writing software does not cope with that huge long stack of operations. So the conventional approaches of having some C++ finite element library, or even worse, having hand-coded the whole thing from scratch, not even using a library, results in the situations where people spend most of their PhD or most of their postdoc just trying to get some sort of solution to the equation, when actually what they were trying to do was be an expert in preconditions or something to do with the application or whatever it was. And so this is fundamentally unproductive. Fundamentally, what we need is a mechanism whereby you can be the expert in the thing that you are an expert in. You can make your contribution in there and have that composed together automatically with the expertise of all the people who are experts in other parts of that stack. And that's what Firedrake's about. And so what we're going to do in these sessions this afternoon is we're going to have a play with Firedrake, and we're going to learn how you use Firedrake to do that, and I will, as we go along, explain somewhat what is actually going on under the hood such that this magic, in big quotation marks, occurs. So we're going to kick off with that right away. I'm just going to check we have one red flag. Okay, so you could try refreshing this help. Yes, boom, we're in. Okay, so everyone pull down your green things, because now we're moving on. And I'm going to start by, so what we're going to do is I'm going to do the first few of these tutorial notebooks with you guys, which are the really basic, this is how Firedrake works. So this is, so if you've not used Firedrake or Phoenix before, by the time we do these, you'll have at least seen how that works. Now, I have 10 notebooks up on that screen, and we have just under 3 hours now, and so we are not going to do 5 notebooks, three and a half notebooks an hour for the next 3 hours. We're not going anywhere near that. So what will happen is we'll get to the break about halfway through, and then I'll have a bit of a discussion with the room about what areas are of most interest to the people who are here, and we'll pick out 2 or 3 of the more advanced notebooks that we're going to do in the second session that give some insight into how those work. And those ones are a little bit less interactive because as you get into more advanced stuff, there's less that I can tell you to do from scratch in a couple of seconds, but there are still interactive things in there. But first of all, let's just start off with the basic stuff. And there's some sort of law that says that if you are teaching finite elements, what you do is the symmetric positive definite Helmholtz equation. So I'm sorry for anyone from electromagnetism who thinks I'm cheating, who thinks that the sign here is the other one. If that sign is the other one, then life is much more complicated because the operator is indefinite and I have to actually care about my solves and so on. So we're going to do the simplest possible case. If you're a fluids person and you have compressible fluids, this is the one that turns up for you. So you also think this is important. But I fully accept that there are other application areas where that's not the case. So I'm solving Laplacian u plus u equals f. So this is the way that the solid mechanics people write this expression. I apologize profusely to any fluids people in the room who is expecting u to be a vector. It's not. It's a scalar quantity. The nice thing about standards is everybody's got one. And so that's definitely what's going on here. So what we have, it's an elliptic operator. So second derivative, vector second derivative of u plus u is f. The reason why we choose to solve Helmholtz rather than the Poisson equation or Laplace's equation with the Poisson operator is because this one is well posed with homogeneous Neumann boundary conditions everywhere, unlike Poisson. So we're making our life as easy as possible. So that means when we do finite element, what do we do? So the bell rings, you salivate, you integrate by parts. And so we multiply by a test function, integrate by parts. And so that produces this guy, which is good because now we only have one derivative hitting each thing, and my H1 finite elements are mathematically make sense. And when you integrate by parts, you get a surface term. So notice the x integrals for bodies, the s for the surface. And this term in here turns out to be the thing that in my boundary condition is 0. So we just cross this guy off. So this is known as the do nothing boundary condition because we literally implement it by doing nothing. And that's what we do. So we're going to start running down this notebook. If you haven't seen these before, these are Jupyter notebooks. They used to be called IPython notebooks. This is IPython running on the cloud and showing its output to you in a web browser. And so on these notebooks, we have cells. So you can see the first cell is outlined in blue because it's the one with focus. And there are two types of cell. There are the cells which contain code, which look like that. And there are the cells that contain documentation that look like this. And the cells that contain code, we're going to want to run. And you can click buttons and things to run cells, but actually Shift and Enter runs a cell. So if I press Shift Enter here, then you saw, if you were paying attention, that in the square brackets, I got a little star. The little star meant that the Python kernel was running, and then it turned into a 1 when it was finished. And in this case, that line is just doing the correct voodoo such that IPython will cause the graphs we're going to make in a bit to appear in the browser. So that's an artifact of doing stuff in Python. So I just keep pressing Shift Enter to get down past these guys. So, so here's the problem we're going to solve having got rid of the boundary term. And we have to choose a forcing function. And of course, what we do is we choose a forcing function such that we know what the answer to the equation is so that we can check whether or not we're right. And so if I want my solution to be this, then what I need to feed in is this. Of course, you do it that way round. So this is a technique which is so ridiculously simple that it shouldn't have a name, but it does have a name. This is called the method of manufactured solutions. So what you do is you take your PDE to which you don't have an analytic solution. You make up the solution you would like. You substitute the solution into the PDE, and you discover that it's not a solution, and there's a residual. But if you add the residual onto the other side, it's a solution. So that way, and so that's an incredibly convenient trick for having analytic solutions to PDEs that you can test. So that's all we're doing here. I substitute this guy into this operator, and I end up with that. So I say, well, obviously f's equal to that. Now I have a well-posed problem. So how are we going to do this with in Firedrake? So Firedrake, at the top level, is a Python module. And so the way you get it is you import it. The way most people use Firedrake interactively is to import star. I realize importing star is a controversial thing to do, but when you're pulling in an entire language that you want to work with, it's actually really, really convenient to do that. So we, from Firedrake, import star. I'm being told off. It's fine. I understand what the problem with from Firedrake import star is, but it's so convenient. Such a good drug. Right, and so also because Firedrake is written in Python and because we are nice, well-behaved people, all of the Python objects that you encounter are self-documenting. So the first thing we need in order to have a domain is to have a mesh. Now, you can read in meshes from your favorite mesh generator, and we might see that a bit later. But a lot of the time for really introductory stuff and even some not very introductory stuff, people want a small set of meshes. They want a mesh of a unit square or a rectangle or the surface of a sphere or something like that. So we give you convenience functions that do that. And so if I say help unit square mesh, it tells me that there's a unit square mesh function which expects to get nx and ny, which is the number of cells in the x and the y direction. It takes a reorder argument that we're not going to worry about. It takes a argument where you can force which way the diagonals are going to go in a triangular mesh. It takes an argument to say, oh, no, I didn't want a triangular mesh at all, give me quadrilaterals. And it has some stuff at the end which is to do with parallel, which you almost never care about. Even if you run Firedrake in parallel, you almost never care. The way you run Firedrake in parallel is you write the script you wanted to run in serial, and you MPI run that script, and Firedrake deals with the rest. Literally no user parallel code. Okay, you can similarly, because it's a notebook, you can get the same information by typing $unit square mesh and it pops up. And that's cute. But let's actually make one. So let's make a 10 by 10 unit square mesh. And well, that executed correctly, and I've now got a variable called mesh, which contains whatever it is that you get when you call unit square mesh. Why don't I have a look at that? So we have a plot function, and the plot function produced a structured unit square mesh. Brilliant. So thus far, we haven't done anything that's actually finite element related at all, because that's just a mesh. So in order to have a finite element solution, what we have to do is choose what the local polynomials are going to look like on each cell, which is called choosing the finite element, and then produce the correct numbering of local degrees of freedom associated with the global topology such that you get one of those polynomial spaces on each cell, and they all connect up together. In Firedrake, we do this by just saying, I'd like a function space, please, on the mesh. And the easy way of doing this is you just pass the rest as arguments here. So CG is an alias for continuous Galerkin. So these are just the scalar continuous polynomial elements. And we're going to do the simplest possible thing. We'll have the scalar polynomial linear elements. So, and now I want to start writing some finite element method. And we're going to do this symbolically. So we're going to write down the weak form of the PDEs in Python. And so I need some symbols. So this now is basically specialized Mathematica. The bits we're about to do are just symbolic calculus on a computer. So I define a trial function and a test function, which are symbols associated with the appropriate function space. Press Shift-Enter. Shift-Enter runs the current cell and moves to the next cell. And similarly, I can get the symbols for the coordinates because I have a forcing function, which is a function of space, of x and y. So I need the symbols for x and y. And the Firedrake mechanism for that is you can ask for the spatial coordinates of the mesh. Having asked for the spatial coordinates of the mesh, then you can write out mathematical expressions that use those, and those symbolically mean what they say. There is a small trap that people somehow manage to get themselves into at this point where they go, oh, I know where cos comes from in Python. It comes from math. So they in order to type this line, they said, from math import cos. Don't do that. That'll break everything. That's Firedrake cos, which means symbolically cos on a Firedrake object, not math.cos, which means actually evaluate the cosine of the number I'm giving you. So there's my expression. Now I can write the actual equation. So this here is the specification of the equation in Firedrake. And so if we compare that to the maths. So here's the maths. It's the integral of grad u dot grad b plus uv times dx is equal to the integral of vf dx. And when I write that here, I have the dot of grad v with grad u plus v times u times dx. So we don't have an ASCII integral sign. There is a Unicode integral sign, but it's not a letter, so it's not a legal identifier in Python. So we can't write the integral out the front, so we write integration by multiplying by the measure. So dx is an object defined in the unified form language, which is the language that Firedrake and in fact Phoenix and in fact some variants of Dune use to define differential equations. And the rest of this is what you would have typed into Mathematica, basically. So it's the equations written out, and there's the right-hand side, f times v times dx. It's conventional in finite element land to call these things a and l if you come from there. We also need to solve the equation. So a solution field is in the UFL parlance called a function. So it's a function in the function space that we define. So we make a function over v. Right, so up until now, this was basically all symbolic. It's not quite all symbolic because this guy and this guy have actual data behind them. At the moment, this guy has a whole load of zeros, but it is actual data. But all of this was just symbols. So now is the point where we actually come to solve a PDE, and we do it by saying solve. So we provide the PDE on the left. For a linear PDE, we say a equals right, so a bilinear form is equal to a linear form. We say which variable we're solving for, and we'll come back to this one in a second. We just run it. Bang. And that takes a few seconds. Why does that take a few seconds? I mean, this is a piddling little problem. At the moment, it looks like I'm trying to flog you a rubbish piece of software that takes a couple of seconds to solve a 10 by 10 Helmholtz problem, which should be solved in probably milliseconds at worst. So, yeah. Yeah. So what happens inside here is a specialist compiler called the two-stage form compiler, TSFC, takes these expressions and does what you would do by hand. So it decides on a quadrature rule. It tabulates the basis functions at the quadrature rules. It substitutes those into loop nests that evaluate these integrals over each cell. Those are then passed through various optimization stages that reorder those loops into vectorizable order, eventually spewing out some C code, which gets passed to the C compiler, and the C compiler produces a shared object. Python links that shared object, executes the code inside, and that produces a sparse matrix and a vector. Then that sparse matrix and vector gets handed to PETSc, which is a massive nonlinear and linear solver library, and many other things, produced by Argonne National Laboratory, which is in itself contains many of the cutting-edge solvers out there, but much more importantly, has through-call interfaces to a very large proportion of all of the sparse linear algebra that is available in the world. And so that then solves the system, and what you get back out again is UH is populated with the solution to that problem. So all of the heavy lifting of solving the whole finite element system happens under there. This is programming PETSc. So these are PETSc options, and we'll see more of them later. So that is essentially a whole different piece of software. So we contribute to PETSc, but we are not the main PETSc developers. And what happens is we simply pass through your programming instructions to PETSc so that you can choose any solver you like. And in this case, because I know that's a symmetric positive definite operator, I've just switched the default Krylov subspace method from GMRes, which it would be, to CG, because I know I can do CG on a symmetric positive definite problem and it's better. We're going to see way more complicated solver options later on. And I plot the solution, and the solution looks like cos x times cos y to me. Because I know the answer, I can also use this code generation to post-process. So actually, solving the PDE is frequently only a small part of your problem. And what we actually really have here is a vector calculus in finite element spaces language, which sort of goes beyond just solving finite element problems. And so that means that I can write down what the exact solution is. I can assemble the interpolation of the exact solution into the function space minus what I got, and I can look at the error. So if you look at the sign here, this is relatively small. It's a pretty coarse mesh, so it's not that small, but it's relatively small compared to the previous one, and you're going to make it smaller in a minute, because now you're going to have a go. What you should do is just go back and change what we did to, first of all, use a higher order, maybe quadratic, maybe a little bit higher order. And secondly, switch to using quads. Find the spot at which you can change to quadrilaterals, read the unit square mesh stuff. Small warning with doing stuff in IPython notebooks if you're not used to this. The instructions execute in the order you execute them in and not the order they're printed in. So if you go all the way back up and change the mesh, you need to run all the other cells in between, because otherwise some of your intermediate results will be on the previous mesh. And at that point, you're going to start throwing errors because you're trying to solve a problem that's half on this mesh and half on that mesh, and Firedrake is not going to be your friend. So do that. When you've done that, stick up your green tag. If you get stuck doing that, stick up the red tag, and I will come around and help you, or maybe Alex will come around and help you. Go for it. Supply you with the magic labels. So when you are done with an exercise and are bored and waiting to go on, you put up a green one. And if you get stuck and need help, you put up a red one. I stole it from Software Carpentry. Software Carpentry tell you to do this. Rerun the cells, yeah. Oh, okay. So it's plausible you've somehow managed to hang the kernel. Let's just So you get occasional glitches in Jupyter Notebooks. I don't really know why. It doesn't seem to have anything particular to do with us. Yeah, you do. Oh, okay. Yeah, that's bad news because you absolutely, so this is running on the cloud. This is not running on your laptop. Oh, that's not good. Yeah, it's plausible that we have, oh no, here we go. That ran. It's just being slow. So 22, right, you can see. So these numbers are in sequence. So they're the order in which the cells have been run. So there we go. So I think that was some combination of the machine at the other end deciding to be slow for some reason and your network going down. I don't know which was which. So I noticed quite a few people are green. Not everybody is green, but I will push you on to the next one. So this is also a kind of pretty simple thing to do that just demonstrates what you do in order to use Firedrake to reason about the problem you are solving, as well as to just solve the problem. And so one of the first things you're going to do when you have a new numerical method is cook up an analytic test solution and check convergence at the correct rate. And essentially, if you've done any numerical PDEs before, you've already done this. This is just an exercise in working out what you have to type in Firedrake to achieve the thing you already knew. So we have an error norm function, and the error norm function, if I clicked on this, would tell me that, now I'm trying to use the network, here we go. We have a function containing an exact solution, a function containing an approximate solution, and it will do the correct integral to work out the corresponding norm. And the norms that are supported are LPH1 HDFH curl. The default is L2, so which is the one you want most of the time. So most of the time you don't need to change that. It's only if you're getting flashy that you need to muck around with that. And so using that to check convergence is as simple as setting up a loop where you compute the error for meshes that are doubling in scale, and then you just use this function to work out what the approximate convergence rate is. Give that a try, and then I'll give you just a few minutes to have a play at that, and then we'll move on and start worrying about systems that have more interesting boundary conditions, which is almost all of them. Yeah. No, it's not actually wrong. It's warning you that it's doing what it's saying on the tin. So when you start using transcendental functions in expressions, the quadrature estimator isn't it's not a very tight bound. Sometimes it's a catastrophically untight bound. So it's just warning you that it's doing something quite expensive by choosing a very large number of quadrature points in order to be safe in getting that thing right. So if you, for example, interpolated uexact into a function instead of using the expression directly, that error would go away because it would know how to do the quadrature correctly. Well, you don't have to. What you wrote is correct. It's just warning you that it's using an awful lot of quadrature to do that job, which on a problem like this you don't care about. No, that's so. If you type what you typed, then that is what will happen. It's essentially us being upfront about the fact that our magic is limited. So what you can do is you can, in various places, you either do the interpolation yourself, in which case the quadrature degree will come out right, or in various places you can set what the quadrature degree is. So if you don't trust us to get the quadrature degree right, or if you deliberately wanted to underintegrate, for example, which is a fairly routine thing, then you can specify that. Which I've just put a massive bang onto. Oh, this gentleman here, I say, excuse me. Shuffle along here. Yeah, okay, so that's what he just got as well. Yeah, so I mean, it's doing what it says on the tin. So if you use a expression with transcendental functions in it in an integral directly, the code which works out how much quadrature is required gets very conservative about that. So all it's doing is giving you a warning that it's used an awful lot of quadrature. So it's used degree 12 quadrature for what is basically a degree 2 problem, because it's basically being overly conservative in how much quadrature you need to evaluate cos. And it's warning you it's doing that because in suitable circumstances, that might be a performance problem that you wanted to do something about. Yeah, so you can't directly tell it in error norm, which we probably should be able to do. If you wrote out the integral, then you can say dx brackets degree equals and force the quadrature that way. You'll only get it once, but you'll only get it once for the slightly different reason that the output of the compiler is cached. So we don't keep calling the compiler every time. Okay, that's the same warning. I'll tell everyone what that is. Oh, what's happening? Right. So lots of people are asking me about this warning that they're all getting if you do the obvious thing here. So it is what it says. It's a warning. It's not an error. What's going on is when you directly use transcendental functions in a form, and the error norm is a form, then the code which estimates how much quadrature you needed in order to do the integrals well gets very conservative. So it puts a lot of quadrature points in because cosines are not exactly representable as polynomials. And so essentially that warning is saying, I'm integrating a quadratic term using degree 12 quadrature, which is very high, basically because I don't know it's a quadratic term, because its intelligence is limited. And in this circumstance, you don't care, because evaluating norms is under almost all circumstances not a performance critical operation. And so if you use a bunch more quadrature than you need to, doesn't matter. If that were turning up in the operator evaluation of a matrix-free solver, that might be a performance critical problem, at which point you might decide to intervene and set the quadrature on the integral. So you can say dx brackets degree equals n and force the quadrature degree. That's also, if you wanted to do under integration, that's how you would force the quadrature degree to whatever you thought it was. And so that's what that pink warning is. So I'm going to move forward because time is flying. And just quickly show you how to do some boundary conditions, because actually boundary conditions are often the critical bit. I have a colleague, Colin Cotter, who's a very good numerical analyst, who says that if he comes home looking grumpy, his wife is a lawyer, his wife says, oh, is it the boundary conditions again? Which is pretty much the story of life. So how do we impose boundary conditions? So we, last time, chose to solve a problem where the boundary conditions were homogeneous, and I could do the really easy thing of just going and dropping them on the floor. So let's take one step up and say we're still going to have Neumann boundary conditions, so it's still grad u.n, but on part of the boundary, which we'll call gamma 1, we're going to set them to an actual value, and on the rest of the boundary, we're going to still drop them on the floor. So that means that this term goes away because that's this one, but this guy doesn't go away. Instead, we use the fact that we know what this much of the thing is. This much is equal to g. So we just substitute g in. So now we have a volume integral and a surface integral, and from the way that I have chosen to write those in the maths, you can probably already work out how we specify a surface integral in Firedrake. So a domain surface integral is d little s. If you're doing discontinuous Galerkin methods and you have interior facet integrals, they are d big S. We're not going to see those today, but you might care. And how am I going to specify what part of the boundary, the domain, we apply the boundary condition to? Well, the answer is that the mesh generator has the job of painting the boundary, so labeling the boundary with integers, and we use those integers. So if you are using Gmesh, for example, I saw Jean-Francois' name on the invite board upstairs. If you're using Gmesh, then you use physical lines and physical surfaces in Gmesh to set what those are, and those numbers turn up inside Firedrake. If you're using one of our inbuilt meshes, the inbuilt meshes specify the numbering of their boundary, and it's in the documentation. So if I look at the help of unit square mesh again, around the bottom here, it tells me that the boundary edges are numbered as follows. So edge 1 is the plane x equals 0. Edge 2 is that one, edge 3 is that one, and edge 4 is that one. And so the way I set up this problem looks almost exactly the same as last time. So that stuff is all the same as last time. But now I set a value of g, and g could be, for example, some sort of sine function, or it could be a finite element function whose values I've interpolated from external data. It could be any of those things. In this case, I'm going to do the simplest thing possible. I'm going to set it to 1. I could literally write 1 there. So people often frequently ask question on Firedrake Slack, what's the difference between 1 and constant 1? So 1 is a literal number which would literally turn up in the generated code. So if you then decided that you meant 2, then the next time this thing runs, the code generation runs again, because the code is different. Constant wraps the thing in it wraps the value in an argument that's passed into the execution kernel. So if you use constants, it doesn't re-trigger. So and in fact, constants are not constant in time, they're constant in space. So a constant means something which isn't a function of where you are on the mesh. So you can change them. So you can use them in time-stepping schemes to put in information like spatially constant values that should change with the time step constants. So, and here, I've just changed my right-hand side to include the extra term. So boundary condition value times test function times ds. And I can solve that problem and do the same thing as I did before. And you should do that, and you should plot the solution, or I can plot the solution. Someone tell me how to plot the solution. There you go. So you're not all asleep yet. It's not very visibly different because you can, if you look carefully, you can see that over this side, the reds are more red than over this side, because all we've done is set the gradient at the edge. So it's not blindingly obvious what the change to the... Okay, let's move forward and let's look at... Yeah. Yeah. Hang on. So DS1. So the 1 here is the part of the boundary I'm applying to. Also, actually, so we don't have areas labeled on the built-in meshes, but if you were using, say, Gmesh and you labeled parts of the domain, then you can use dx with a number in it, and it will only integrate over the relevant part of the domain. So that applies if you have material properties which are discontinuously different in different parts of the domain, for example. Okay, so let's look at Poisson, because Poisson now is ill-posed with only Neumann conditions. So now, in order to make this have solutions, I either need to deal with the null space, and we can deal with the null space, and if we choose to do the multi-grid exercise later, it shows you how you deal with the null space. But the other way of making this problem well posed is to have at least some Dirichlet conditions. So Dirichlet conditions are different. So what are we doing here? We're setting up a problem which is here the same as it was before, except no mass term. Right? So just minus Laplacian in U. And here is the sort of boundary condition we had earlier. And here is the Dirichlet condition. So here is set the value to what I'm going to tell you to have on the boundary. And how are we going to do that? So we set up the same problem as before. We set up the same sort of, it's not the same actual function, but materially the same sort of exact solution as before, and materially the same sort of problem. And now we need a Dirichlet-BC object. So the reason why we need a Dirichlet-BC object is because Dirichlet boundary conditions are not applied by changing the form, which is what happened with Neumann boundary conditions. They're applied by changing the function space. So you change the function space to a function space that only admits functions which satisfy the boundary conditions. And the way you do that is by removing the relevant boundary nodes from the PDE and solving the algebraic equation value equals boundary condition on those nodes. So that amounts to replacing the corresponding rows of the matrix with identity rows, and you put the boundary condition value on the right-hand side. I'm currently lying, by the way, but I'll explain it this way first, and then I'll tell you what we really do. And then what you do is you forward substitute those values so it also takes out the column. Actually, for the benefit of people who know what this means, that's really not what we do. What we really do is we treat all linear problems as nonlinear problems, and we use a Newton solver, and in the Newton solver, we set the initial guess to satisfy the boundary conditions, and we zero out the corresponding rows and columns. And that just means we do less operations. And it means that we only have one code path, so we do the same thing for linear and nonlinear. But mathematically, what I told you first is exactly correct. That's what we're doing. So what we're going to have to do is specify an object, which we call Dirichlet-BC, and the Dirichlet-BC object modifies the function space in the solve call in order to produce a solution which satisfies the Dirichlet boundary conditions. And so, as before, we're using boundary IDs. This time we're using a list of boundary IDs, or a tuple of boundary IDs. And so what does a Dirichlet-BC object look like? It looks like the function space we're modifying, the value, and here I've used a literal 0. You can put a finite element function in this function space in here. You can put a expression in x and y in there. Basically anything which is legal UFL can go in there. And this is where it's going to apply. So it's a pretty simple object. And I give that to the solver. So I don't modify the function space all the way up there. And the reason I don't modify the function space all the way up there is because actually the function space is really only being modified for the purposes of the solve. And once I've solved, I'm back to the original function space. So really it only makes sense to say, for the purpose of this solve, change the function space in accordance with the boundary conditions. So that's why that turns up in the solve, not in the specification of the function space. The rest is the same as before. And I get a solution, and that solution pretty obviously has 0 boundary conditions. So I did something right. So have a play, and just do this very simple case here. So this very simple case here, we set one value on the lambda1, which is the bottom, another value on the top, and Neumann on the sides. So when you do this, it has the really boring solution, which is a straight line that goes from the top to the bottom, right? But you just need to work out how to, so you have to make 2 boundary condition objects for this one. There is actually a full write-up of how we really do it. If you go to Dirichlet boundary conditions, there is in fact a full write-up that tells you exactly how we really do Dirichlet boundary conditions. And if you follow that through and think carefully, you can actually work out how adjoint boundary conditions work, which is quite cool, because adjoint boundary conditions are traditionally regarded as being really complicated, and they're actually not. So where people get themselves into trouble is they think that what you do is you zero the rows and columns, and that's not really true. What you do is you zero the row, and zeroing the column you should think of as a precondition operating on the matrix. So it's some sort of incomplete LU precondition, right? It's forward substitution. And so as soon as you understand that that's a preconditioner, then it's kind of obvious that the matrix you're supposed to adjoin isn't the one with the column zeroed out, it's the one before you zeroed out the column. And as soon as you do that, you get the right answer for what the conditions are. You don't necessarily implement it like that, but that tells you mathematically what you're supposed to do. I told you it wasn't a very interesting outcome. Is that the error? The do nothing boundary condition. I hope no one's going to try and implement the do nothing boundary condition. I mean, you can if you already want. You can add a constant 0 times. Sorry? Should what be equal to 0? 0. Give people just a minute or two, and then we'll move on. Yeah. You should definitely make sure that you don't have PETSc-dir and PETSc-arch set. So you should make. So do you have a PETSc other than the Firedrake one installed? Okay, then I shouldn't have a problem. So you can break Firedrake by pointing it at another PETSc. So PETSc looks for particular environment variables, and if those environment variables are set, then it will find an unsuitable PETSc and wow, there's a lot of Okay, I'm going to move on a bit then, because I think a majority, but I accept by no means all of the group have got there. Decisions. Which of these do I want to do? I'm trying to remember what that one is. Oh, that's vector valued. I could do that. So, should we look at a vector value problem, or should we look at a nonlinear problem? What do you think? We have votes here for nonlinear. Let's look at nonlinear problem. Okay. So this is one of the versions of Burgers equation. So Burgers equation is like fluid dynamics without the pressure. So nothing's enforcing any sort of incompressibility or compressibility rules. So you just have an advection diffusion equation for momentum. So it's nonlinear because you're advecting momentum, so you've got u times du dx. So it's one of the simpler things you can do that is a time-varying nonlinear problem. So we get to see both how you make the time-varying equations and how you deal with nonlinear equations. So the spatial discretization, so this one's a 1D problem, which makes our life kind of easy. So discretization is really straightforward. So if I integrate by test function v and take the second derivative term and integrate it by parts, this is what I get. You'll notice I have dropped the boundary terms on the floor. The reason I've dropped the boundary terms on the floor is because I'm going to use a periodic domain, so I'm going to really cheat. But you can get to see how a periodic domain works in Firedrake as well. So I don't have any boundaries. If I don't have any boundaries, I don't have any boundary conditions. Isn't life great? And then in order to minimize the number of symbols I need to write on the board, I'm going to use backward Euler. I'm not necessarily recommending backward Euler as a time-stepping scheme for most purposes, but it has the advantage that I only have one u here, not some combination of u's. So it just keeps the number of symbols on the board low. And so I need a domain, and I need initial conditions. So we're going to have a periodic interval, and I'm going to put a sine wave on a periodic interval. So how do I do that? Well, I use a different built-in function for periodic interval mesh. For those of you who have used other packages, there is, in fact, in Firedrake, no such thing as a periodic boundary condition. In Firedrake, there are periodic meshes. So how does that work? Well, the mesh topology is continuous around the periodic domain. So if you ask in the mesh topology who are your neighbors, then when you get to the appropriate point, it says all my neighbors are this guy and that one over there. But then the coordinate field obviously has to jump when we go over the corner. And the way you do that is in Firedrake, coordinate is just a finite element function. So it's normally a function in vector linear space, but it can be quite a lot of finite element spaces. So in particular, you can use a discontinuous function space for the coordinates, and that's all we do in the periodic meshes. And most of the time, they are in fact continuous, but only by coincidence. And then when we get to the point where it jumps, there's a discontinuity in the coordinates. And because in the finite element method, you only ever take a difference between two coordinates inside the same cell, that just works. So that means actually in our code, there is no support for periodic boundary conditions at all. You just feed in a periodic mesh and periodic works. So this is a convenience function for cooking up a periodic mesh. This guy you've met before, the spatial coordinate, I'm only taking out the 0th component. So even in 1D, the spatial coordinate is a vector. It's just a vector with only one entry. And I'm making this constant viscosity. I'm going to, for the hell of it, use quadratic elements this time. And I'm going to need, because I'm going to be time stepping, I'm going to need a next velocity and a current velocity. So these are just functions which are in this space. The names have no technical effect in Firedrake. What the names do is they enable us to, when we print these guys out at various points, know which one we're talking about. So but they are there for human consumption. And I once again interpolate my initial conditions just like I've done previously. I'm setting a sensible dt value. So now I write out the residual of my problem. So so if we look at this, so I've defined v as a test function, and u and un plus 1 as functions. There's no trial function. Right, so this is the one-form residual. So this is something which, when you evaluate it, gives you, strictly speaking, a cofunction, a dual function, which is 0 if the value of un plus 1 is a solution, and non-zero otherwise. That's what the residual means. So here is my residual form. So once again, times v's. The time stepping is just written out. So there isn't a magic way of specifying time steps in Firedrake, basically because the maths for that hasn't been done. So there are time stepping abstractions out there. None of them deal with a significant subset of the cases that real users come up with. And so at the moment, for us and everyone else in realistic cases, you have to write out the time stepping because no one's come up with a good enough mathematical abstraction. We are also going to want the results, and because we're running a time simulation and I'm going to want to make a pretty animation, I'm going to want to record a series of all the results. So all I do is I make a Python list, which I put my initial conditions in. And here I'm exploiting the fact that if you call function not on a function space, but on a function, it's a copy. So this is how I can have a copy of my initial conditions before I overwrite them. And then finally, I just loop over time. So what's going on here is I solve the problem. Now look how I'm solving the problem. F equals 0. So nonlinear problems, you write down the residual, you solve residual equal to 0. So what's this going to do? Well, it's going to do a bit more than we did previously. It's going to, so under the hood, Firedrake will differentiate the residual symbolically. So now I have the Jacobian, which is a 2-form, and it will use SNES, which is PETSc's nonlinear solvers, to do some form of generalized Newton. And you can program that using PETSc options if you want to, as to what it does. The default is a form of line search Newton. And so we call over to SNES, and SNES calls back to Firedrake to assemble Jacobians and residuals as required, and then PETSc solves them, and when that converges, we can nut. That's the magic under the hood there. And then what we do is we take the new solution and we override the old solution. We put a copy of the new solution onto that results list. We increase time, and we go around again. Simples. So that takes a little bit of time, mostly because the compiler had to run again. If I ran that again, it would go through much quicker. So that's running all those time steps. And here we always get this out. So here is my initial conditions. And what actually happens because of the advection term, the solutions to Berger's equation are steepening and eventually form shocks. So if I run this along, what I notice is this turns into this kind of steeper and steeper sawtooth wave, which is the... Now, what I've just shown you is correct but slow. And the reason it's slow is because I've got to solve inside the time stepping loop. So every time I hit that line in the time stepping loop, I do all of that calculus again. I make a new PETSc nonlinear solver. I don't do all the code generation again because we cache code generation, so that won't rerun. But that cost is significant. When you start, so if I were writing a fluids model and the linear solves inside that nonlinear solve were A and G, I I have to set up the whole AMG hierarchy again every time I go through there, right? That's really not good. So instead, you provide a mechanism for providing a solver object which you can keep calling solver, so that you don't have to rebuild the solver every time. And so the way we do that is a two-step process, basically because we inherited this notation from Phoenix. So anyone who's used Phoenix is having like an amazing deja vu experience. Firedrake is deliberately Phoenix compatible whenever we can be, because it is just insane to generate another user experience, right? It should be the case that if you've learned how to use Phoenix and you've learned how to use Firedrake, you can essentially swap between them as you need to on the project you're on or whatever. So there are incompatibilities, but the incompatibilities occur when we come to the conclusion that we don't have a sane way of staying compatible with Phoenix. We try very, very hard to not do that. So what do? I make a nonlinear variational problem, and the nonlinear variational problem is the bit that takes the maths. So it takes the residual and the solution, and if I was doing boundary conditions, they would go in here as well. And then I make a nonlinear variational solver, and the solver takes in the problem that I made and potentially solver parameters. So here's a bit more PETSc language. So earlier we were using CG. Well, CG is not going to work on this guy, but it's a piddling little small problem. So the correct thing to do is to use a direct solver. How do I use a direct solver in PETSc? Well, you have to understand PETSc's model of what a linear solver is. PETSc's model of a linear solver is a Krylov method with a preconditioner. And the preconditioner itself can have a preconditioner, and then it totals all the way down. And so what's the Krylov method for a direct solve? The answer is a direct solve isn't a Krylov method. So in PETSc's world, a direct solve is just a really, really, really good preconditioner. So what you do is you say, my Krylov subspace preconditioner type is pre only, so only run the preconditioner. And my preconditioner type is LU, which is the direct solver. So I do that, and then I write pretty much what I had before. It's just instead of putting that solve line in there, I put my solver in there and I call it solve method. And the solve method will solve with the current values of everything that was specified in that form. So as I update UN here, it will cause the correct value to be used the next time around. And we'll just do exercise 1 here, because then we will just about have time to go through another notebook before the end of this session. So what you should do is, so the notebook magic time it times the current cell. So we very carefully set these cells up in the right way, so that if you chuck time it into cell 13, and you chuck time it into cell 9, and rerun the cells, so percent time it, like it's written at the bottom, then it will run it. But notice, you need to up your mesh size, because if you run it on really small meshes, then all you're seeing is overhead. So you want to go back to the beginning, redefine the mesh to be bigger, run all the cells, and then time those two cells and see how they compare for speed. Sorry, I should have seen your red flag. Yeah. So dx is the measure. That's exactly the same as Phoenix. So that's how we write integral. Because we don't have an integral sign. You just multiply by the appropriate measure to show integration. So times dx's are volume integrals, and times d little s is a surface integral. And
this is one y versus u and the
so in the finite element method, you're solving a variational problem. So you're taking variations against a test function. So that's what v is. And the unknown solution problem function in a linear problem is called the trial function. So these are the symbols for the unknown solution function and the unknown function that you are testing against.
So this A represents this stuff here?
That A represents that operator, yeah, on the left-hand side of the equation. Well, the weak form. So it represents that integrated, multiplied by v, integrated by parts. So using a Dirichlet boundary condition. So Dirichlet conditions are represented by changing the solution space to one that only has solutions in the right space. So the Dirichlet boundary condition object, Dirichlet-BC object, represents a modification to the solution space that's going to be used in this solve. And so it's a modification to space V. It's to set it to value 0, and it's on boundary IDs, which is in fact the whole boundary, because this mesh only has 4 boundary IDs.
Okay, so for this exercise here, if we want to change this, we have two boundary conditions.
So you have 2 Dirichlet-BC objects, and you pass a list of them.
And we change this one
To 1 and 2, okay. Yeah.
How can I make a list?
So it's just Python. So just
Okay.
like brackets.
Okay, cool.
Yeah. Oh, lost the. Okay, so we will have a quick look at. Yeah, we've got 10 minutes. We'll have a quick look at the mixed Poisson problem. So everything we've looked at so far is solving for one scalar variable. And that is not what most of the PDEs you actually care about look like. Very, very often we're solving systems of PDEs. So we have, we're solving fluid, and we have velocity and pressure, and maybe temperature and salinity if you're an oceanographer. Or you're doing mechanics, and then you have displacement fields and energy fields and so on. So everywhere we go, we get mixed systems. So the simplest mixed system, so we can do a demo, is what happens when we decide to take the Poisson equation again, the one we already met, and do the PDE equivalent of what you learned as a first-year undergrad to split a second-order differential equation into 2 first-order differential equations. So or at school if you went somewhere flashy. So what do? We introduce a new variable, which is called sigma, and the sigma is defined to be equal to the gradient of u. So sigma is going to be vector valued, because the gradient of u is vector valued. And so now we can substitute in here. So we have divergence of sigma is minus f, sigma minus grad u is 0. So I have 2 equations in 2 unknowns, and I still have the same boundary condition choices I had earlier, except that because sigma is defined to be the gradient of u, Neumann conditions on u now turn into Dirichlet conditions on sigma. Right, conditions on the gradient of u are conditions on the value of sigma. So I get essentially the same system I had before, but split into 2 chunks. And any of you who've done fluids or structures will realize that actually that's something you very often really want to do. And so I can get a system to solve for this. In order to do that, I need now not 1 function space, but 2 function spaces, because I need a function space that u lives in and a function space that sigma lives in. And at the very least, they differ by the fact that the sigma function space has got to be vector valued, and the u function space is going to be scalar valued. And in fact, in order to have stable finite element schemes, they typically vary by a lot more than that. So here is my system, my weak form. So there's sigma and there's u, and then that's the test function for u, and that's the test function for, sorry, wrong around, that's test function sigma, that's test function for u. And so we're going to solve this problem, and we'll just make our life easy with the boundary conditions and set u0 equal to 0, and we choose an appropriate forcing function, which I've written down there. We don't really care what it is. So I make a unit square mesh again, because it's my favorite. And we're going to use a stable function scheme of the type that is, depending on which community you're from, either known as a compatible discretization or a finite element exterior calculus discretization, or maybe just people know it by its element name, which is Rabiotoma. So Rabiotoma is a vector valued function space that lives in the Sobolev space HDiv. So that means it has continuous normal components and discontinuous tangent components, which is, it turns out, exactly what you need to be allowed to take divergence, which is the operation I need. And then the V space, the scalar space, what I would think of as the pressure space, because I'm a fluids person, is discontinuous. So linear discontinuous elements. So elements that are linear but jump between cells. So I do that just by declaring those function spaces, but I'm solving for both of them at once. So what I actually need is a combination function space that has both of these in it. What we call a mixed function space. Mixed function space is a horrible term because it's still a mixed function space if both of the function spaces are identical. But that's what they're called in finite element land. And so the way we do that is that the multiplication operator is defined on function spaces. So when I multiply together the two function spaces I define, I get a function space W. And now, instead of writing test function, I write test functions. So this is quite important. Taking the test functions of W is not the same thing as taking the test function of sigma and the test function of V. The reason it's not the same thing is that these test functions know that they are indexed test functions that are part of W. So when you assemble the system, they know which block of the system they're supposed to be assembled into, which wouldn't be true if you just took the component parts. So we do it. So we have to do it this way. You can, if your conditions ask for it, ask for test function W, and you get a mixed test function. That's a perfectly mathematically well-formed thing to do, but it's not the way most people write down PDEs. So normally people want the individual bits, and they write down the PDEs in terms of both parts. Forcing function is just like it was before. Now let's look at A. A has got all the terms in it. So A is the whole mixed system added up together. So these guys are terms from the first equation, they have taus in them. And these guys are, this is a term from the second equation. And that's the whole right-hand side as well, it's just that one of the right-hand side bits is 0. And that works because in the finite element method, it is always 100% necessarily true that every form that turns up in your residual or your Jacobian contains exactly one test function. So the presence of the test functions in these expressions is sufficient for Firedrake to be able to pick them apart and know which equation they belong to. So you just write down the whole system, add it up together. The solution lives in the mixed space. So the solution has a sigma part and a u part. And the way we get that is we declare a function over the whole mixed space. So this is a function which has got 2 bits inside it. It's a function over a mixed space. And we run solve. And solve looks exactly the same as it does before. I've used a really awful solver there. The reason I've done that is because this is a big indefinite system. Right? And if we choose to make that choice after the break, we'll come back and do better things for this. It depends what notebooks people want to run after the break. But we can look at the solution. Okay, this bit, and this is where so I try to avoid being rude about the Phoenix people because the Phoenix people did something absolutely amazing that we've got to lift lots of work from. This is the single biggest mistake in the entire design of the Phoenix interface. If I have a coefficient function which I need to use in a form, and it's from a mixed space, and I want one of the bits, the syntax is split of function. If I have a function in a mixed space and I want to look at its contents, I need to do function.split. So split of function and function.split do subtly and importantly different things that will just cause you to make mistakes and do errors. It is horrible. I'm very sorry, there's nothing we can do about it. Someone else designed that bit of the API. So here, I have my solution and I split it, and then I can plot the bits. Because obviously it doesn't really make sense to plot something in a mixed function space monolithically. So that's the scalar, and there's the vector. This is using our inbuilt plotting stuff. Alex has much prettier plotting stuff than us, which we need to steal. Cool. So it's half past, so I'm not going to go into improving solver performance for a couple of reasons, not least which is that, well, one, we don't have time, and secondly, if we want to do that, the composable solvers sheet is better afterwards. So we're taking it's a half-hour break, is that right? Yeah. Right. So, so up here are, so 10 is probably not so interesting, but the options that we could look at after the break, and we'll get through some of them, are how you can automatically solve PD constraint optimization problems, Firedrake, how geometric multigrid works, how flashy composable PETSc solvers work, so how you program the whole PETSc linear and nonlinear solver system, and how to do hybridization. So if you know what HDG is or hybridized compatible methods, we have support for that as well. So after the break, I'll sort of take some sort of straw poll about which of these we're going to go through. But now we'll take a half-hour break. Okay, so we're back on. So bang on time. You're all like really well trained at this. Okay, so as I mentioned, what we're going to do in this hour-and-a-half session is we've got those notebooks that are left, and we'll look at as many of them as we get through, and I'll ask you in a minute which ones we should try to get through in this time, depending on your interest. Before I do that, I will just cover a couple of things about how Firedrake works as a community in case you are sufficiently impressed by what's going on that you decide that you want to have a go. And so, funnily enough, we're a software project. We've got a website. And the website has a bunch of things which are useful. So we have download instructions. We have quite a lot of documentation. So these notebooks are here. That needs updating, but that's basically true. If you wanted to start playing Firedrake yourself and get more into it, the best thing to do is install Firedrake and start working down these tutorials. There are also more advanced ones at the bottom here if you know what it is that you're after or particular features. There's a certain amount of manual documentation as well, which is useful. So I pointed out this earlier. If you actually want to know how Dirichlet boundary conditions works, there's a manual chapter that tells you how Dirichlet boundary conditions work mathematically in our implementation. The other really important thing on here is the contact page. So when you start using Firedrake, you're learning to use a completely different language, also one that was written by normal human beings. So if it is not breaking, you are not trying. And so when it does break, you need help, and we provide you with multiple mechanisms for getting help. Normally, the best first port of call is the Slack channel. So there is a magic link there that gets you invited. So Slack is irritating that you can't actually have officially public Slack channels, but there are third-party hacks that manufacture invitations. So if you click on the link there, you get an invitation, you get into our Slack channel, and basically everyone who works on Firedrake and a lot of our users passively hang out there. And if you ask questions there, at least in hours that people in Europe tend to be at work, then you rapidly get answers from the people who best know, which is good. There's also a mailing list that you can post stuff to and ask about. And we run everything through GitHub, and we actually really like GitHub issues. And so often the first port of call is to go to Slack and say, this is what's happened, because it may well be that you've just made an error. But once it becomes clear that you've actually found something that we have broken, then it's really, really helpful if you post issues on GitHub, because we've got them there and we go back and we fix them. Especially in the install script. Install script's really important. So that's all of that. We're going to go back to doing a bunch of this stuff. The last thing I'll do before I do it is I'll pass these around. So 2 years ago, I went to SIAM CSE, and I went to a Julia tutorial. Julia is a really cool project, by the way. But the main thing that I learned at the Julia tutorial was that if you have stickers, then people go around and advertise your project for you. And it turns out this works. I now turn up places and I see people's laptops with Firedrake stickers on. So I brought along a Firedrake sticker, so I'll pass those around, and if anyone feels inclined to put a Firedrake sticker on their laptop, then I would be, like Alex already has, then that would be absolutely awesome. See, I've got mine too. So what do we want to do? So we can look at inverse problems, PDE constrained optimization, and how that works. We can look at multigrid, we can look at composable solvers, we can look at hybridization. We're probably not going to get through all 4 of those in an hour and 25 minutes. So what are people most interested in? Sorry? Optimization? Anyone else? Not necessarily, but all right, let's do optimization and we'll come back to the others. I think I get the vibe that there's a bunch of people here who do inverse problems. Well, like science and engineering are about inverse problems, right? So a simulation is a little model world, and you put the inputs in and you see what happens. And there are circumstances where prediction is what you were trying to do. That is how the weather forecast works. But actually, most of the time in science, you know what happens, you want to know why. And in engineering, you know what you want to have happen, and you want to know what you were supposed to do that. So actually, inverse problems are completely pervasive in science and engineering. And so it's really important that we provide people with the tools to run inverse problems as well as forward problems. And the way we do that is with Firedrake adjoint module, and the Firedrake adjoint module is actually just Dolphin adjoint. So there is a separate package called Dolphin adjoint that was originally written by Patrick Farrell and me and Simon Funke and Elizabeth Rogness, Marie Rogness, from Simula, and it made adjoints of problems written in Phoenix completely automatic. But as you've already noticed, we look a lot like Phoenix. So in modern Dolphin adjoint, there's a very thin compatibility layer for Dolphin and a very thin compatibility layer for Firedrake that makes Dolphin adjoint work on top of either of them more or less equally. And what does that do? Well, let's have a look. So, as usual, we do the magic matplotlib command, we import Firedrake. Now, the next thing I do is I import Firedrake adjoint. Why am I doing that? Well, the way that an adjoint simulation works is you run the transpose of the linearization of the forward simulation. And when you have a time-stepping system, if you consider the whole time-stepping system as a one big system, it's block lower diagonal, which is to say the current time step never depends on a future time step. It only depends on itself and previous time steps. When I transpose that to run the adjoint, I discover that it's block upper diagonal. So in the adjoint variables, you only ever depend on the future state, not the current state. So what you need to do to run an adjoint problem is linearize your problem. Well, we've already seen that Firedrake can do that because that's how we solve nonlinear problems. And you've got to be able to run it backwards. And the way you run it backwards is you have what's called a tape. tape records all the operations you do. And in conventional AD, that tape is recording like every plus and every multipliers and every tiny operation that you do. In Firedrake adjoint, Dolphin adjoint, that tape is recording every time you solve a PDE. So each PDE you solve in your time-stepping mechanism, and also other mesh-sized operations like doing assignments when I'm doing explicit time-stepping and those sorts of operations. And so then, when it's recorded all of those, it can unwind them in order to compute the adjoint. How does it do that? It does it by using overloaded versions of solve, assign, interpolate, all of the things that change values. So what's happening here is Firedrake gets imported, and then Firedrake adjoint gets imported, and it overwrites a whole bunch of the Firedrake names with the Firedrake adjoint versions. So now when you type solve, you're really getting the Firedrake adjoint version. And what does the Firedrake adjoint version do? It records that the solve is happening, and then calls through to the Firedrake. So let's do our problem. So we are going to minimize what's called the compliance, which is the L2 norm squared of the gradient of the velocity plus a penalty term for what's going to be our control, and I'll show you what that problem is in a minute. For Stokes, because it's easier to solve Navier-Stokes, and we want to do this quickly, given these Dirichlet boundary conditions on this mesh. So hang on, let me show you the mesh. So this is the first time I'm not using a mesh from one of our built-in toy mesh classes. So we ran gmesh. There's the mesh file. So mesh of a gmesh file gives you that. And if I plot that mesh, it is a channel with an island in it. And if we go back up here, so I have no flow on the top and bottom. I have a prescribed forcing at the inflow. I have pressure is 0 at the outflow, which is the usual outflow pressure. And I have U equal to some unknown function G on the island. So this is a flow control problem where we basically attempt to minimize this functional by sucking or blowing out of the circle. So how do I do that? Well, I set up my forward problem. So here's Stokes. This is the weak form now. I've integrated by parts. That double dot, for anyone who hasn't seen it before, means inner product, because this is a vector, so when I take its gradient, I get a tensor, so I have a 2-index inner product going on there. And here's my inflow, there's my no flow, that's my control, so that's the guy I'm going to be solving for. And, oh, I'm going the wrong way. So, that is the function spaces, the mixed function space for the pressure velocity system, test and trial functions, all of those boundary conditions I just talked about. Now, how are we going to do this controlled boundary condition? So what I do is I set up a function in the finite element space. So this, in principle, has values everywhere, but we're only going to care about the ones that are on the boundary. And I make a Dirichlet boundary condition. This is how you do Dirichlet boundary conditions on mixed systems. So this is a boundary condition on the 0th subspace of the mixed space. So in this case, on the velocity. There's the value. And if you looked at that mesh, the island is boundary 4. And I just add this guy onto my list of boundary conditions. I set up my bilinear form, which looks exactly like the ones we've been looking at the whole time. And I say solve. And this time I'm just going to smash this guy with a direct solver. That's not necessarily a really great solver for a fluids problem, but this is a small problem, so what the hell. Something you need to be aware of when using a direct solver LU on a mixed system is in PETSc, you can make a mixed system where you just have one big matrix and the blocks are just rows and columns in the big matrix. Or you can make what they call a map nest, which is a nested set of matrices. And if you want to do manipulations with the blocks, the nested set is better, and that's Firedrake's default. The problem is nobody's direct solver works on nests. So if you want to use a direct solver on a mixed system, you have to change the matrix type. And AIJ is what PETSc calls a CSR matrix. I don't know why they call it AIJ and not CSR, but that's what it is. And so that's telling it, make one big monolithic matrix so that LU will work. And that's an internal optimization for LU's parameters we don't need to go into here. So this then is the solution to that system. So I get velocity, the velocity speeds up as it goes past the island, which is not a huge surprise. The pressure is higher upstream of the island than downstream of the island. That is, once again, not very surprising intuitively. So what I'm trying to do is minimize effectively the curvature of the velocity, the gradient, the curvature of the velocity, subject to not wanting to do too much sucking and blowing. Right? So the g-squared term is saying that more changes to this boundary condition are bad. How do I do that? Well, I have to define a functional that I want to optimize. And basically, that functional can be any scalar valued thing that you can calculate from Firedrake quantities. So the way this works is when you have Dolphin adjoint imported, assembling a zero form, so assembling an integral that doesn't have any unknowns in it, no longer produces a float, it produces an annotated adj float, and operations on adj floats annotate themselves, so if you add things to adj floats, that gets annotated. And so the adjoint system has a full record of how you computed those values. So what I do in this case is, here's my functional. So that's a zero form, that's a zero form. I add together two zero forms, and I have a zero form. I assemble the zero form, and I have a number. In this case, an adj float. So that's J. I also, because I'm going to be taking the derivative of my PDE with respect to some, the derivative of the functional of my PDE with respect to some control, I have to tell Firedrake or Dolphin adjoint what the control is. So in this case, the control is that boundary condition function. So M is G labeled to be a control. And so a reduced functional in optimization speak is the optimization functional considered only to be a function of the control. So J is also here a function of the solution of the PDE. So implicit in this is the go away and solve the PDE step in evaluating the functional. The reduced functional just looks like this. So that's symbolically setting up that problem. And now to minimize that functional using the default optimization algorithm from scipy.optimize, you run that one line. So what's happening under the hood there is it's computing the adjoint problem, using the adjoint problem to compute dJDM, feeding that into some sort of gradient descent algorithm, going around again and iterating on that until it converges. So what happened? I got an answer. The answer is the new control value. Right? So J hat knows what its control is. When I run minimize on J hat, I get out a new value of that. And I can plot that. And if I plot that, what I discover is, well, it's 0 almost everywhere, which is not a surprise, because it only actually does something when it's being the boundary condition. And on the boundary condition, these big arrows pointing inwards mean it's sucking in flow mostly around the front of the island. And what does that really mean? Well, one thing we can do is we can see what it did to the functional. So remember I declared J hat as the functional. So J hat works like a function. It has its call method overridden. So if I provide a control value into j hat, it will evaluate the functional. So evaluate the functional implies that it goes away and solves the PDE again, right? That happens under the hood. So printing j hat of g and j hat of g opt will solve the PDE twice with different values of g, and it will give me two values, and I can see that that one's a bit better than that one. So in some sense, some sort of optimization has occurred. And if I want to know what that actually did, what I can do is just solve the PDE again using the new value of g. So I just assign the optimized value of g into g and run the problem. If I had set up this problem as a linear variational solver, I could just call solve on the solver. What I'm doing here, notice this guy. So the tape is still running. So if I call solve, then Dolphin adjoint will believe that I'm adding more solves onto the tape. And I'm not really doing that. I just want to rerun the problem to have a look at it. And so I am going to tell it, don't watch. Just don't concern yourself with the thing I'm about to do. And so the optimized pressure looks kind of similar to what we had earlier, although if we look at the axes, it goes up to 14 over here, and it only goes up to about 6 over here. So actually it's really rather different. And you can see that the velocity is rather different, and that's because a whole bunch of it's getting sucked in at the front. And this isn't actually a very interesting optimization problem, but it does demonstrate quite how simple it is to solve an optimization problem. You can also have all the bits. So you can call, this gets dangerous because I'm going to start live coding, which is always asking for trouble. So if I can call compute gradients, G, nope, this is always dangerous, M, there we go. Then, oh, that hasn't worked either, okay. That'll teach me to attempt to live code this. But essentially, if I had read my manual correctly, compute the gradient of a objective function with respect to a control and with respect to a tape. So possibly I was supposed to say there you go. Okay. So if I tell if I don't want to outsource the whole computation of the optimization somewhere else, if I just want to plug these things into an optimization algorithm, I have the bits. So what has this done? It has run the forward PDE, run the adjoint PDE, contracted the adjoint PDE with the JDM, and that gives me the gradient big D, J, dm. You can do the same thing to get the Hessian. If you think that's a sensible thing to do in your optimization, right? So one of my favorite lines about Firedrake is I can't fix maths for you. So if you tell Firedrake to do something which makes any sort of mathematical sense, it will try to do it. That doesn't imply it was a good idea. So if you ask it to take a second derivative of something in a DG space, it will quite happily locally compute the second derivative of everything on all of the cells. The fact that that is in almost all circumstances a junk number isn't my job. Right? And there's a good reason for that, and that is that I can't predict what you actually want. And it turns out there are people who have something useful to do with that number. So we can't magically work out what was mathematically a good idea. We just give you the bits that you can use And if you decide to shoot yourself in the foot with them, that is your prerogative. So that's how this guy works. So the last thing to look here is, so I told you there was a tape. In fact, we can have multiple tapes lying around. And sometimes that's useful if you need to have multiple optimization problems on the go at once. And you can switch what the current working tape is, or you can do more than one optimization problem in sequence in your code, and you can drop everything off the current tape. So you can clear the tape so that you can start again. So that is a little bit magic. So the tape is effectively a global variable, and global variables are usually a bad idea. But the only alternative to having a global variable is having the user say at every operation which tape things were supposed to be on, and that would require the user to annotate everything, which would completely undermine the huge usability benefits of what we actually have here. So that's this guy. This is kind of going quicker than I thought it was going to, actually. Right, what should I do now? What should I look at? Hybridization. Okay, the votes of hybridization. Okay, so this gets, so now we're going to do some maths. Okay, so mixed systems. So we've been doing a bunch of solves in mixed systems, and we've been doing it in dumb ways thus far. So the first one, if you remember, I built the whole mixed system, which is a huge saddle point system, and I hit it with min-res. And when I went to solve the optimization problem, I said, oh, it's a small problem. I don't need to worry about this. I will just make one monolithic matrix and smash it with LU. So that's just great. It's not going to work for a big system. It's really not going to work in 3D. Direct solvers in 3D are going to run your machine out of memory really quickly, and you're going to get very bored waiting for them to finish. So there are better ways of doing this. And the better ways of doing this quite often revolve around doing what's called a Schur complement. So what does that mean? So suppose I want to solve our favorite expression. So this is ever so slightly more complicated than mixed Poisson. This is actually a linearized rotating shallow water equations. So this is, so if I just kept this term, and this term, I would have mixed Poisson with some scaling factors. So this guy is a velocity, and this guy is, this guy is a, sorry, what's the, and D is a height. Right. Okay, here he is. If I put this guy in, I'm now compressible. So now instead of solving for div u being 0, divergence in velocity causes the surface to go up and down. So that's effectively a compressibility term, or in this case, it's the water height, but that also looks like a compressible term. And that guy is Coriolis. So because we're operating in a rotating frame of reference, because the Earth spins, then at large scales, acceleration occurs at right angle to the force. And that's what that term's doing. So there is the simplest thing, which is recognizably equations from an ocean or atmosphere model. The reason why we were actually playing with this set is because the UK Met Office is in the process of rewriting all of the weather and climate models used in the UK, and we need to work out how to make the solvers work. We're using the same sort of mixed space we did earlier. So we have an h-div velocity and a discontinuous surface height or pressure space. And these guys are, so this is in residual form. So that, but the thing you care about is this. Don't worry so much about that one. So we're trying to solve this system. So if you look at the colored terms, so the terms are colored by what the test function and what the trial function in each of those terms is. So you get a block system that looks like this. And it's a saddle point system, and it's indefinite, which is kind of horrible. But we're going to do that. So we define some constants. These are constants which make sense in the context of doing simulations on the surface of the Earth. the radius of the Earth, for example, at some average. And for this, we're going to need a more interesting mesh. So we also have utility meshes for the surface of the sphere, because we do lots of ocean and atmosphere work. And the one that the Met Office are interested in is called the cube sphere mesh, which is what happens if you take a mesh of a cube and you blow it up like a football so that it becomes spherical. And so this thing has a radius, it has a number of times to be refined from the original cube, and it has a degree because it turns out that representing a sphere as a polyhedron isn't a very good representation. So we are bending the element out to match the surface of the sphere in order to have lower error. So we make one of these guys. For technical reasons, so once you have a immersed manifold, so a manifold of a two-dimensional object floating around in 3 dimensions, it's not straightforward to work out which way is up. So you can't locally look at the mesh and work out which way the up direction should be. And so you have to tell those class of meshes which way is up. Otherwise, the pullbacks don't work for edge development. And so in this case, what are we doing? We are taking the spatial coordinates. So here, x is the full coordinate vector. And we are telling the mesh to set its orientations to the spatial coordinate. Why are we telling it to choose the spatial coordinate? Because the spatial coordinate is a vector field which points outwards from the origin. And so at every point on the surface of the sphere, that will be what we conventionally think of as up, at least if you live on the surface of a planet. So that's what that's doing. And what you get is a thing that looks like this. So Matplotlib's 3D plotting is kind of a bit limited, but hopefully you can see that that is a sphere that's made up of little squares. So as mentioned, we're using some excitingly exotic elements. So that's your pressure space. So it's linear on each element, it's continuous between them. And this is RTCF2, which is the Ravia-Thoma cube element with face degrees of freedom. So it's the HDiv1 as opposed to E, which is the edge degrees of freedom. So you have continuous normal component of velocity that varies linearly on each edge. And you have additional components of velocity that are stored inside as degrees of freedom. This is a more exciting space. So this is where having code generation really comes into its own, because implementing these guys and implementing PDEs containing these guys gets really tedious really fast. So we just say, oh, it's another finite element, we're using it. That's my Coriolis term. Here are my equations. All of this is exactly what you've seen before. So now here's my linear variational problem, like we explained earlier. And how am I going to solve this? I'm not going to solve this by smacking it with a direct solver, because that will be eventually really slow. Like on little toy problems, it's fine, but eventually that's going to suck. So what I do instead is I do Gaussian elimination on the blocks. So the inverse of the whole system is given by this upper diagonal system hitting this thing at the diagonal, hitting this lower system, where S is the thing called the Schur complement. And the Schur complement is what you get by eliminating the first variable into the second variable. So that's why it has an inverse of the top left-hand block. Problem. A is a sparse matrix. A inverse is really not a sparse matrix. So if I was going to really assemble this guy, I have two options. I can do it matrix-free, and every time I want to multiply by this matrix, I have to solve a linear system inside. You can do that. There are circumstances where that's the right thing to do. Or B, I would have to assemble a dense linear system the size of a PDE, which is not feasible. So I have to not do that. And so a traditional approach is to say, okay, if I use this guy not as a full solver but as a preconditioner, can I get a good enough approximation to the inverse of this such that it's a good preconditioner? And it turns out that a good answer is if I approximate a mass matrix by its diagonal, then something quite good happens. It turns out to be something that's a bit less good, as we'll see in the rotating frame. So now, so remember earlier I said we were programming PETSc. This is what programming PETSc really looks like. So here's my linear variation problem. This is my stuff, and this is the stuff which is in the PETSc language. This is me just passing straight through to PETSc. So what is PETSc's programming model? So PETSc's programming model is you have a Krylov subspace method and a preconditioner, and preconditioners themselves frequently contain solves and further preconditioners. So it's a nesting structure. So what they have are traditional key value arguments combined with a prefix concatenation operation. And the prefix concatenation operation enables you to have solvers inside solvers. And it turns out that an arbitrary combination of solvers inside the solvers basically enables you to do anything in linear and nonlinear solver space. So what does that mean in this case? So let's start at the very beginning. KSP type, GM res. So the outer system is not a symmetric system. So you can't use CG, so we use GM res. And we're going to set a relative tolerance of 10 to the minus 7. And I'm setting a massive number of maximum iterations. This should give you a warning that this is a crap preconditioner, by the way, because I'm going to give myself a lot of space here. So preconditioner type is this Schur complement. And that in PETSc land is called the field split preconditioner, because I take the fields and I split them up. So PC type field splits, and then, so this is where the concatenation options starts. So once I've set the PC type field split, now there's a prefix called PC field split, which contain the options that pertain to this guy. So in here, the type of the field split preconditioner is, like I told you, a Schur complement. The Schur factorization type is full, which means I'm going to do that full expression up there. And then I have to start worrying about how to do A inverse and how to do S inverse. So A inverse is field split 0 and A inverse is field split 1, and that comes from the order in which I specified the fields. And, okay, so now I get, so the fact that I've said field split means I have the field split 0 and field split 1 prefixes. If you've used PETSc before, by the way, you won't have seen brackets before. So if you use PETSc directly, you would actually have to write PC field split underscore type Schur, PC field split underscore Schur fact type, and so on all the way along. And when you get down here, the options get about this long. So if you see a talk by Matt Nepley, you get these whole screens full of PETSc options. And so we decided that we were too stupid to read that, and we figured that we might have some users who were too stupid to read that as well. So we put in brackets. So what actually happens under the hood is before we give this to PETSc, we expand the brackets out. But that makes this a lot easier. So field split 0 is a solve, right? I'm inverting that matrix onto the right-hand side. So it has its own KSP. It has its own Krylov method and its own preconditioner. So its KSP type is going to be pre only. The reason for that is because, remember, this is approximate A inverse, and approximate A inverse is is equivalent to just doing ILU. So ILU is incomplete LU, and so that gives me so that inverts approximately the mass matrix. And now I need the solver for the outside solve. The solver for the outside solve. So the reason I did all this in the first place is what this guy really is, what this guy is, and therefore this guy also is undoing the original splitting of my elliptic problem into two parts. So I started off with the Helmholtz problem. I introduced a new variable to make it into two equations. I discretized those equations, and now at the discrete level, I'm putting them back together again. So after doing the substitution, this guy is an elliptic operator. And that means I can do nice things like multigrid. So here, this is this is GAMG, which is PETSc's own algebraic multigrid. And I think G stands for generalized algebraic multigrid, which is them attempting to claim that they're better than everyone else. It's just a multigrid solver. And when you have multigrid, what you do, well, it's algebraic multigrid, so you call some of the operators, and then you have to smooth at each level. So you have to tell it what smoothing to do, and we're going to do 5 Chebyshev iterations with Bloch-Jacobian ILU as the preconditioner. So that's just something you would do. So that whole mess sets up this problem. And now, because I've made this system, I can just call solve on it and wait for a while, because it's quite big. Should have thought about this. Last time I ran this, I was using my colleague's MacBook Pro, and this was a bit quicker. This is the MacBook. It's the one that only weighs about 900 grams, and it's basically powered by a gerbil on a wheel. Okay, so it's solved. And it's worked because if I look at the residual of the problem afterwards compared to the size of L beforehand, it's 10 to 10 smaller. So we have really solved that system, not very quickly. So because we've got the solver object, and because PETSc are like a serious professional outfit, that solver internally records lots of things about the solve process. So it records how many sub-iterations took at every level, what happened to the residuals, all those sorts of things. And we can inspect the solver object to find out what happened, why that was quite so boring. And so what I'm going to do here is, so the solver contains a SNES, which is a PETSc nonlinear solver, which contains a KSP, which is the linear solver, and KSPs have an iteration number, and they have a reason why they converged. And so if I print those guys out for this solver, I discover that there were 5 outer GMRes iterations, and quite a lot of inner ones, and we converged because the relative tolerance, so the drop in the residual compared to the original residual, was good enough. What happens if I start increasing beta? So beta, way up here, is let me show you. It's not very easy to see. So beta is a term which is increasing the extent, the rate at which Coriolis varies with latitude. So basically, it's changing the scale at which we're solving this problem. And these are all reasonable values of beta if you're really solving the ocean. So at beta's 4,000, it now takes 7 iterations. Beta's 8,000, it takes 12 iterations. At 16,000, it takes 27 iterations. At 32,000, it takes 74 iterations. And at 64,000, it's taking a while. So 589 iterations. So this solver is very, very, very intolerant to being used on bigger and bigger ocean problems. And remember, all of those values of beta are completely legitimate problems an oceanographer might really want to do. So it turns out that that approximation wasn't very good. One of the reasons it's not very good is that that mass term that I'm approximating isn't just the mass. It's got the Coriolis in it, and the Coriolis term is completely off diagonal. So that preconditioner was ignoring the fact that I was making the Coriolis term worse and worse and worse. So all of the work in solving the Coriolis was getting picked up by the outer GM-res iterations, which really sucks. So I'd like to actually invert that block, right? Because then I'll have the off-diagonal bits in there. But it's continuous. So this is where hybridization comes in. So if that were a discontinuous block, then in a discontinuous method, if you don't have any derivatives, your degrees of freedom are only locally connected to each other. So you can invert the mass matrix, and in fact the Coriolis matrix, locally on each cell. Yes. So let's just make the velocity discontinuous. So what I do is I take my original space, so then my original space looked like this. It's a slightly different rendering of it. And it has shared degrees of freedom on the edges. That's what makes the normal component of the velocity continuous. I just split them. I just decide that the normal component of velocity here doesn't have to be the same as the normal velocity component of velocity here. Great. Now I've got a discontinuous pressure. Of course, velocity mass matrix. What I've actually done is I've turned a system that used to solve the equations over the whole domain into a system that individually solves them disconnectedly in all of the elements. And by the way, the boundary conditions aren't right, so it's not even well posed. So what I do now is I put the connectivity back in again. And the way I do that is I introduce a new space which is only defined on the edges and has the same number of degrees of freedom as the normal components of velocity that are supposed to be linked up. And I write a new equation which says that the velocity is continuous. So one way of understanding this is when I did this, I'm solving the PDE on each cell with strong boundary conditions, Dirichlet boundary conditions, connecting each cell to each other. And in this case, I'm solving the PDE on each cell with a weak boundary condition, an extra equation for the boundary condition between the two. So what does that look like? So here, this is a sum over all of the interior facets of all of the cells, everywhere in the mesh, not just on the surface, of u dot n. So that guy is imposing that the jump in u dot n is 0. That's what that equation says. And it does that by defining a Lagrange multiplier lambda, and the adjoint of that operator turns up in the original equation. So straight down the line, Lagrange multiplier maths. So now, I've just made everything worse. Because now my system isn't a 2x2 block diagonal system, it's a 3x3 block diagonal system with many, many, many more degrees of freedom, because all of a sudden, this guy has lots of separate degrees of freedom that used to be shared degrees of freedom, and I have all these degrees of freedom that are reimposing the continuity. So this looks awful. It's not awful, and the reason it's not awful is because of that thing with the sparsity pattern. So this is what the sparsity pattern of the original system looks like, and you can kind of see where there are elements here. So this is for a tiny mesh with only 4 elements. But you can also see the couplings of the normal components of the velocity. And you can also see then the pressure and some coupling terms there as well. And there's the pressure mass matrix, because the pressure is discontinuous. That's block diagonal, so that's easy to invert. This is the sparsity pattern of the hybridized system. And so here I have, this is the mass plus Coriolis. This is the pressure. These are the coupling terms between the pressure and the velocity. And if I take this guy plus this plus this plus this, that is a disconnected pressure velocity system on one cell. All the coupling between cells turns up in these Lagrange multipliers that are on the outside. So now I can do exactly the same Schur complement trick, except that instead of trying to eliminate this block, which I can't do because it's not block diagonal, I treat all of this together as the block I want to eliminate. And that means I get the inverse of that block system hitting onto these guys. But this guy is element local. So what I can do is I can loop over the mesh, visit each cell, assemble all of these operators, do this inversion, multiply these together, and add them onto the outside. Well, I could, except that, and this is where people who write conventional finite element libraries get really shirty about people who write high-level abstract systems like Firedrake. They say, Firedrake's fine as long as you only ever want to solve a toy problem, and then you want to do something complicated, and I don't even know how to write that down in your silly language. And they would be right, except that a really great PhD student called Thomas Gibson, who's just about finishing, wrote an extension to the language for doing local linear algebra on locally assembled forms so that you can write this out. And so what he did is this. So here we have V hat, which is a function space on the broken element of V. So we have a symbolic operation where you say, give me a UFL element, give me a finite element, and I'll give you back the one that's been discontinuized. The other space is still what it always was. There's the space of the Lagrange multipliers, which is what's called a trace space, because it's actually on the trace of the original element onto the facets. And now I can make a three-way mixed space, get my three-way test and trial functions, write out the system using my new V hat and U hat, and then I have a new piece of language which you haven't seen before, which is tensor. So tensor wraps a form and gives me access to the locally assembled tensor. And I can get the blocks out of the locally assembled tensor, and I can do linear algebra on them. So remember, what I wanted to do was this here. So I wanted to take this guy, invert it onto these guys, and this is what that looks like. So I take the last column, first couple of rows, onto the first couple of rows and columns inverted onto the first two columns, last rows. And what do I get? Well, I get what you always get in Firedrake, a symbolic expression. So that's a symbolic expression for the calculation that's going to be done. And you can actually assemble that. That would assemble, and it assembles the system for the trace space with the elimination in there. And it turns out, what's the trace? Trace is effectively a term that's penalizing a jump in velocity. What does a jump in velocity look like? It looks an awful lot like a finite difference approximation to the gradient in the velocity. What's the gradient in the velocity? It's the pressure. So that's a very hand-wavy argument which can be made much more rigorous. And the rigorous version is that the trace space is another approximation to the pressure. And it's spectrally equivalent to the pressure system. So it's symmetry positive definite, its eigenstructure is the same as the pressure system, and you can do all the same nice tricks on them. Now, you can do all this and write all of that out, but this ends up being boilerplate code. So you had your mixed system, and your mixed system isn't exactly the same as my mixed system. So you weren't solving shallow water equations, you were solving Euler, you were solving whatever other system. And there's a recipe. The recipe says, take my incoming elements, I break them up, and I take my original bilinear form, and I put I replace the test and trial functions with my modified ones, and I add on these jump terms that are reinforcing the continuity, and then I do this operation. So now we're back to the thing that Firedrake is supposed to make go away. We're back to people having recipes of code that they have to keep re-implementing all the same way. So that's bonkers. So obviously we're not going to do that. So instead, what we do is we give you a new preconditioner. Because hybridization is nothing else than a preconditioner, right? It's an operator which takes in an original system and gives you back another system which is better to solve. Nothing else than a preconditioner. So the way you actually do this from Firedrake is you make another massive set of parameters. So what does this set of parameters do? Hang on, let me pull that down a bit so I can reach it. So outer system, the original 2x2 system is the outer system that we're solving. And we're now going to do an exact Schur complement, right? We're going to really invert that mass matrix. And an exact Schur complement is an exact solve of the system. So that's like a really big, sophisticated direct solver. So, direct solver. The outer solver is pre-only. The matrix type is map-free. Why is it map-free? Well, it's map-free because we're never going to assemble the original system. So in the original system, it's a matrix-free solver. So we just tell PETSc, don't bother to assemble the original system. We've got you. We'll look after it. Now we're going to need something a bit more sophisticated. And the a bit more sophisticated is, it turns out PETSc is so cool that you can write your own preconditioners in Python and have PETSc call them. So we write a preconditioner, and through various through various tricks that we do under the hood in Solve, that preconditioner gets passed to not just the numerical problem that Python wants to solve, but also the UFL forms. So that preconditioner has access to the symbolic problem. So then there's just a piece of code which does that stuff inside there. But the consequence of that system is a system is the trace system which has to be solved. So once again, nested preconditioners. So inside the hybridization, so this guy defines a new prefix hybridization, and it's got a KSB type. Because of the way that we're doing the nonlinear, this stuff, the algebraic multigroup preconditioner may not hit the convergence threshold on the first run. So we're going to wrap GMRes on the outside, although we expect GMRes to do very few cycles. Algebraic preconditioner. This stuff is, so this is an instruction to the algebraic preconditioner that the graph of our matrix is symmetric, which is an optimization. Relative tolerance, again, the same multi-grid options that we used earlier. And let's do it. So here's the simple one again. And this is taking a while because now the code compilation problem got way worse. Right? So you have to do the measures involved in generating the code to both produce the local operators and then do all the local linear algebra on those operators in the right way, shove the stuff out. It takes a lot longer. So this takes quite a lot of seconds to go through the code generation interface, but it's cached. So if you were doing this because you actually wanted to solve an ocean or an atmosphere problem, that's a time-stepping problem. So you do that once. So who cares? So that's happened, and we get reduction in the residual. And we don't, I mean, we got that before, and it's about the same as what we got before. So we do the same thing. We set something up to print out what's going to happen. now we're printing out the iterations on the inner system. Because remember, the outer system is an exact solve, so there's only ever one of them. So the interesting thing is what happens inside. And so now, first problem, well, that was the easy problem. 4 GMRes iterations converged RTOL. 8,006 generation is not quite level. 16,009 iterations, 32,018 iterations, 64,041 iterations. So if you remember, using the approximate show complement, that was 589 iterations. And let's just check. So if we take the second to last one of these and find out how long it takes, running time it. So this is the original problem. And so that took basically a second each time. And if we do it using the hybridization solver, it takes half of that time. And that was for an easy problem. On problems the size that the Met Office cares about, it's actually about 10 times faster. And that really matters. So, I mean, that's a cool piece of numeric analysis, but actually, for those of you who are asking questions about hybridization, so those operators are sufficient to get you hybridization of feat methods like this. They get you most of HDG. So it's HDG as long as your flux terms are symmetric, and there are corner cases where that's not true. It gets you LDG. It doesn't get you CDG. In order to have CDG, we would need to do the extra legwork to enable you to write tensors not centered on cells, but on the 2 cells adjacent to a facet. And that's in principle possible, but no one's done the hard work. Okay, so that is, I realize the room's getting quiet. It's 4 o'clock. It's very, it's very warm. We have half an hour to go. What do we want to look at? Geometric multigrid, composable solvers. Anyone got a preference? Still wait. Proceedings. Okay, let's do multigrid. That line is false. I just saw that before we did it. It's not true. Multigrid works in 3D. We just haven't updated that warning for a while. Okay, so geometric multigrid. So thus far, we've used multigrid solvers on a bunch of occasions, but it was always algebraic multigrid. And algebraic multigrid, from our perspective, is easy because we assemble a matrix, and some nice person out there has implemented algebraic multigrid, and we just tell them to do it. When you have geometric multigrid, you can't have a black box like that. So in geometric multigrid, what you do is you coarsen your residual, and then you smooth it with your operator redefined on each level of the coarsened mesh. And so there has to be an interplay between what the solver is responsible for and what the PDE library is responsible for. So we're handing back the problem between Firedrake and PETSc backwards and forwards. And so we need a framework which enables that to happen. The first thing we need for multigrid is a mesh hierarchy. So we start off with a very coarse mesh, and then we refine it up until something very fine. You can now, thanks to Patrick Farrell in Oxford, also set up non-nested mesh hierarchies in Firedrake and have non-nested multigrid work. But stuff we're going to talk about here, this is going to be the introductory version. We're just going to use properly nested meshes. So you make a coarse mesh. So this is a rectangle mesh which has 15 cells in one direction, 10 cells in the other direction on a domain which is 1.5 by 1. And then you make a mesh hierarchy. So a mesh hierarchy takes a coarse mesh and produces a list of meshes, each one double the resolution of the previous one. And it also, under the hood, knows how to construct the operators that go between those meshes, which is the important part. So there's our mesh hierarchy. And so the mesh hierarchy is a Python iterable. It looks like a Python list. So if I ask how long it is, it's 4, because I took a base coarse mesh and I refined it 3 times. And the last thing in the hierarchy is the fine mesh, which is in conventional GMG, the thing I'm going to define my problem on. And that is, and so in Python notation, the last thing in the list is just the -1th entry. So now we have, so what we do is we make a hierarchy, and then we pull out the fine mesh and set up our problem on the fine mesh. So we could do this. I think we should do this because you've all been sitting there passively for ages, and we do have 25 minutes to get through this notebook. So I think that you should actually do this. Why don't you so have a little go, and then I will have a go. The hierarchy still contains the course mesh, so that would be mesh 0. Yes. Oh yeah. So if you wanted to go back and edit the coordinate field, it would be edited in the. I mean, that's an entirely fair question. I'm not entirely sure that we thought through the implications of that. But so the default position is to not randomly copy mesh size objects because they're big. If it's a coarse mesh, it should be all right. But, so should we have a go at this? So what am I supposed to do? I need an interval mesh. So mesh equals. Okay, so that's a really coarse. Let's make it slightly less coarse. There's a unit interval mesh, and now I need a mesh hierarchy. So H is I'm really ruined in typing the word hierarchy in English because of German, I can't believe that a word that is pronounced hierarchy is spelled IE. It's got to be wrong, right? So now okay, so thus far I've what have I done wrong there? Is that the way it works? Expression, no, it's the other way around. Okay, so thus far I've just done stuff that we've done already. What do I need to do? I need to move this function to the course mesh using both restrict and inject. So, what does restrict do? Restrict find dual, course dual. So I guess that means I need whoa, I got something. So, oh, we have the magic in. Why not? Oh, there we go. What happens? Why is that true? Does anyone know? It is right, by the way. It's just the artifact of what restricts does. Yeah, we told, so the instructions tell you to start with the course one and restrict and go that way. So the reason why this is happening is because restrict is not the operator you think it is. Restrict is the dual operator to prolong, and prolong is the one that interpolates. And the reason that works is because every function which is in the find space is also in the core space, but the other way around is not true. So when you prolong things, you end up with what you started with, and that works on functions. When you restrict, what you're doing is you are not actually interpolating from the find space to the core space. You're applying the transpose of the interpolation operator in the other direction. And that is a weighted sum of the values, but it's a weighted sum of the values weighted by the basis functions. So it works if the thing you're trying to restrict is not a function, like the function x that I'm trying to do here, but a integral, which is what happens when you restrict in the multigrid method. And so the reason why this kinks down at the end here is that the weight associated with the end boundary, the end test function is only half a test function. And so if we were restricting a integral, it would be right to add only half of it in that place. The same thing, by the way, would be happening down here. It's just that it's multiplied by 0. So if I, in fact, said inject, and inject is something you hardly ever actually do. Inject is actually the thing that's an interpolation operator. So then you get what you thought. But what happens in multigrid, geometric multigrid, is you prolong values and restrict residuals, which are dual values. So you prolong fields and you restrict integrals of fields. And so that's why those operators are in fact the right ones. If you don't get that immediately, it took me weeks to get my brain around that concept. It's quite counterintuitive. Okay, we're going to solve essentially the same problem we've been solving all afternoon. It's Stokes again. This one's steady Stokes, so there's no time term. So we just have viscosity, pressure gradients, divergence. We have pipes, which means that we're going to be squirting stuff in a couple of chunks on the boundary, and which we do by just setting conditionals. We're going to wimp out, and we're going to stop. We're not going to try and do clever things like HDiv elements. We're just going to do Taylor Hood. So Taylor Hood is continuous quadratic pressure, continuous quadratic velocity, continuous linear pressure, which is another known stable mixed pair. And why is this still here? Go away. So we make a solver, and I'm not going to do this in full detail because we have seen many of these before. I am going to show you something that you haven't seen before. I'm going to point out this bit. So this is how you do case statements in your UFL form. And this might be a little surprising at first if you've done any Python at all, because this isn't what logic statements look like in Python. And the reason for this is that the logical operators and if statements, including the ternary operator, are some of the very few things in Python you can't overload. So it's not possible to have your own and. It's not possible to have your own value if conditional else false value. Those are built into Python. So what does that mean? It means that if you were to use Python built-ins at this point, they would evaluate at this point based on the truth values of the symbols, not the truth values of their values at runtime. And you would get what we could reasonably call junk. So in order to store a symbolic representation of logical operators, we have to use a syntax which isn't Python's one, and the one thing we can always do is define functions. So UFL defines a conditional function, which works like if in Excel, if it's a conditional function in Excel, and we define or and functions. You can overload these guys, so that works. They are overloaded in the right way. But so that's there. Everything else here you've seen before. As vector you haven't seen before. As vector takes scalar values and turns them into vector values. There's also an as tensor. It does what it says on the tin. Do say boundary conditions on one component. A zero with a shape. So there's a few things you haven't seen here before, but they are all kind of fairly obvious. We make a linear variational problem. We make a linear variational solver with parameters given by, well, the parameters are going to get passed in. So we can run this, and now we're actually going to make it. So the first thing we're going to do is not multi-grid at all. First thing we're going to do is just make a monolithic matrix, smack it with LU, like we previously said. So that works. This is now taking a while because the compiler's running, and then the solver's running. It's not a very big problem, so it won't take that long once the solver starts, but the compiler might take a little while. Compiler has got slower in recent months. The reason why the compiler has got slower in recent months is because we put in a whole new backend, which is way better at vectorization. So there's a trade-off between how long it takes to run the compiler compared to how fast the code is, and most users care more about how fast the code is. Okay, so we ran that. We can look at the answer. And so it looks like what we were expecting. So we have flow coming in and out through two entrances, and because it's Stokes, it sort of flows through the middle in a sort of smeared out way. Right. This is not a useful solver technique because it's LU on a mixed system. So what are we going to do for this? So we want to do a share complement method. We've seen those earlier. And we're going to use geometric multigrid on the velocity block and a pressure-weighted mass matrix to precondition the share complement. So this is a known preconditioner class. So in order to do that, we have this trick of, so in order to have a different mass matrix in the preconditioner, we have another custom-defined preconditioner. And this one is, well, we're making it here, but it descends from one that Firedrake gives you. So an auxiliary operator preconditioner is a preconditioner that you use when you want to just shove in a different matrix as a preconditioner. And so the different matrix I wanted was a weighted mass matrix. So I just put that operator in as the form on the subclass of here. And now, all of that stuff we were talking about with the prolong and restrict, I mean, it's kind of useful to know they're there, but as a user, you don't care. PETSc's multigrid is going to access those. As a user, what you do is what we did before, and this is written in the PETSc style options where all of the things are written out. So KSP type GMRes on the outside, because the outside system is asymmetric and we want to demonstrate we've won. So one good debugging trick is even if you think that your inner solve should be a complete solve, you put GMRes on the outside, because then what PETSc will do is solve the inner problem and then check the residual to see if it needs to do another GMRes step. So you were expecting it to do one step, and if it does more than one step, then it's flagged that something's not quite there yet. KSP monitor is a thing you you switch on to get more output from PETSc. PC type field split you've seen before. PC use auxiliary matrix is true. And then PC field split type sure, P field split type sure factorization type is lower, so we're using this bit. And then first field split is multi-grid, so that's what we're doing on the velocity block. The second field split is it's pre-only because we're going to directly invert the mass matrix because that's cheap. And it's pre-only using a Python preconditioner, which is the one we built there. So we built our own preconditioner that we're shoving in here, and it's there. So this thing here is the name that PETSc should import. And because this precondition is written directly in the interpreter, the module that it's in is main. Usually, if you're writing a piece of software, this would be in some module that you've written, right? But if you're just writing it out in a notebook, it looks like that. And so we can solve that, and once again, compilers are running and rubbish like that. And that ran. There is no point at this point in trying to time these as being different because it's not a big enough problem for you to notice. So this is all slightly artificial because it's a 2D problem where a direct solver is a good idea. These notebooks exist in order to show the operations. We're not going to do the exercise, but I will briefly explain this last one here. So that was, in some senses, the simplest multigrid. We can compose together PETSc solvers any way you like, in a way that is as complicated as you like. And this one is basically Lawrence, who is the guy who owns the multigrid code, going to town. So what he's going to do is, instead of using share complement on the outside and multigrid on the velocity block, we can use multigrid on the outside and share complement as a smoother on each level. So on each level, we're going to build the share complement and use it to smooth the system. And so when you do this, it is the case that because you are using iterative solvers on the inside of the operation, you can't use straight GMRes on the outside, basically because your subspace is being perturbed by the error in your iterative solvers inside. So you have to use FGMRes, flexible GMRes on the outside, because that is resistant to the subspace inside moving. So that's what he's done. The matrix type is now nest because we are going to do the share complement on it. PC type is multigrid. So the coarse KSB type, so the one on the outside is, sorry, the one on the inside, the one you're going to do last when you've gone all the way down to the coarsest problem you're going to hit directly. That's a share complement. The full share complement using LU on the velocity part, the zero part, which is going to go fast, and Richardson iteration on the pressure part, where, and then on each multi-grid level, the precondition type is a field split, it's a share complement field split, it's upper, and we're going to solve the pressure with block Jacobian IOU and the pressure using the same precondition that we did earlier. And so we've just completely reorganized the entire hierarchy of how that's going to do by programming PETSc's options. And that also works. So it's 28 past. So I should wind this up there because it's time for that. I am happy to hang around out the front here and answer questions for as long as people want to, within reason. My train's at 7:30. And yeah, I think that's it.